Rather, there is an intrinsic quantum gap between how quantum computers work and our ability to explain them in a single concrete terms. The quantum gap is what made it hard that for me to answer the people request for a concrete explanation about that quantum computing. The right answer to such request is that the quantum computers cannot be explained in a simple concrete terms. If they would be a quantum computers would be directly simulated on the conventional computers, and the quantum computing would offer no advantage over such computers. So in fact, what's truly interesting about quantum computers is understanding the nature of this gap between our ability to give a simple concrete explanation and what reality is going on. So that is an overview of that today's topic. So the quantum computing research, actually so many that research is going on, even still we are under that infant stage. So with this short introduction, I am starting my session. So the overview of today's session is actually go with that what is quantum computing and what does a quantum computer do, how does computing work, and what's the outlook for quantum computing, how the challenge for quantum computing, how the quantum computers are being deployed, and what are the real world applications for quantum computing, and how the getting quantum computing ready for the prime time, and finally conclude my session with final thought. So this is the overview of today's session. So next half an hour we are going to discuss about all the way, we are going to discuss about these things. So first, briefly I want to explain what is quantum computing. So whenever we are talking about the quantum computing, currently the computers are made with silicon transistors. So these transistors are getting smaller and more powerful with each passing year. However, there is a physical limit to this technology. So in these type of circuits, if the conductors are too close to each other, the electrons can bounce between them. So moreover, if a transistor is too small, the electrons can go through the gate of the transistors. So this phenomena is known as the quantum tunneling and can run the entire circuit. So that's why the quantum computing is a sophisticated approach to making a parallel calculation. That's a very, very important. So at present we are under the process of that all kind of parallel processing. So that's why the quantum computing is a sophisticated approach to making the parallel calculations using the physics that govern the subatomic particle to replace the more simplistic transistors in today's computer. So it's clear that uncertain behavior of the quantum particles, that's based on that physical things. So some kind of uncertain behavior of quantum particles is a basis for of the physical limits of silicon circuits. So that's why the scientist that invented a new computer technology with this uncertain behavior of quantum particle, that is known as the quantum computing. Even though the quantum computing it is not an absolute replacement of the silicon computers, in specific cases it can provide the unbelievable processing power. So normally in that traditional system we are using bits are used to store the information data in a computer. But when the transistor is active, it is a 1, and it's whenever it's inactive, it's a 0. That's why the formula 2 power bits represent the number of combinations of bits can create like that. But whenever the quantum computing, a quantum particle is used as a bit in a quantum computer, that is called as a qubit. So it would be an electron or a photon or any kind of particle, but outer electron is that pass plus atoms are commonly used. So here it is a 1 when the spin is up and 0 when it's down. So that spin can be controlled with an electromagnetic field. So far, it seems like quantum and silicon computers are very similar, but the quantum particles are mysterious. So that's why the spin of electrons can be made up and down when we are not that observing. They can be up and down at the same time. So this is known as the quantum superposition. So that's another important term. So hence the quantum computers can provide incredible processing power. Because of this, it's clear that the quantum computer is not a substitutional for a classical system or classical computer. there are particularly designs for the parallel processing. For example, a quantum computer won't be able to give the additional speed for day-to-day work. Occasionally, it would be it may be or it would be slower. The quantum computers can be used for database searching because they can search many paths at once. Thus, they greatly reducing the searching time. And next, the development of quantum computers would affect the data security. Like normally, whenever we are talking about the data security, the encryption is very important. So the encryption is used for the data protection. So to break an encryption code, you will have to force it. Even a supercomputer will take the trillions of years to do that, but a quantum computer can do it in a short period of time. So next, the simulation are used by the scientists to predict the behavior of weather, space, that DNA find in a DNA calculator. The simulations are somewhat time consuming because there are millions of calculations. That's why the quantum computer can reduce the time it takes to run the simulations, because they can perform the millions of calculations at once. And another thing, the quantum computers need very specific environmental conditions, and we can't observe inside the processes when they are running, as it will damage the superposition. So these are the overview. This is about that quantum computing. And next thing, what does a quantum computer do? Actually, already I told you that qubit is very important. So using the qubits, the quantum computers would bust through the calculations that would take the classical computers a long time, if they would even finish them. For example, the today computers use 8 bits to represent any number of data between the 0 and 255. So thanks to that feature, that is like superposition, a quantum computer can use 8 qubits instead of the bit 8 qubits to represent every number between the 0 and 255 simultaneously. That's very important. That's why it's featured like parallelism in computing. All possibilities are computed at once rather than sequentially, providing tremendous speedups. So while a classical computer steps through a long division calculations one at a time to factor a human enormous number, so a quantum computer can get an answer in a single step. That's why that means the quantum computer would reshape whose field like cryptography. So that are mainly based on the factoring. What are today impossibly that any kind of large numbers like that. So that's why that's a very important idea behind that. What does the quantum computers do? And next, how does the quantum computing work? So that that actually in that the starting slide itself, that just I asked that question, how does the quantum computing work? So as per that quantum computing, actually we don't expect to build our own quantum computer like a DIY PC with parts scavenged from the discount bins at the local electronic shop like that. So in that case, the handful of the systems operating today that typically require the refrigeration that create the working environment just north of the absolute zero. So they need the computing artic that to handle the fragile quantum states that power these systems. So based on that, the quantum computer will take the nano Keplernian muscles to create something that is called as the entanglement. So that's when the two or more qubits exist in a single quantum state. A condition sometimes is measured by the electromagnetic waves just as a millimeter wide. So that's why the crank-ups that wave with had too much energy and you lost the entanglement or the superposition or both. So the result is a noisy state that is called as a decoherence, that is equivalent in quantum computing of the blue screen of death like that. So that's a thing. And next thing, what is the outlook for the quantum computing? So here actually they're predicting the quantum future from the year 2010 to 2030. So here there are a handful of companies such as Alibaba, that Google, Honeywell, IBM, so and so on. So that company they operate yearly versions of the quantum computers today. So today they provide the tens of qubits. So that's they are using the tens of cube in terms of 10 power. So they are using the tens of qubit, but the qubits can be noisy and making them sometimes unreliable. So to tackle that real world problem reliably, systems that needs tens and hundreds of hundreds of thousands of qubits. So experts believe it would be a couple that decades before we get to a high fidelity era when the quantum computers are truly useful. So that's why the predictions of actually in this diagram, in this figure, that prediction of the quantum future, the predictions when we reach so-called quantum computing supremacy, the time when the quantum computers that execute the task that classical ones can't, that is a matter of lively debate in that industry. So that's why that actually usefulness of that threshold and quantum supremacy. So that is a thing that's the outlook for that quantum computing. And next, the challenge for the quantum computing. So one of the major problem or major challenge being faced by the today's quantum computer is that it's entangled qubits quickly became the decoherent with that respect to the qubits. So therefore, an algorithm needs to quickly get its work done before the qubits become decoherent. So currently, most quantum companies can only keep a few tens of qubits coherent. So a recent study that I have shown actually it's represented in that some article that cosmic rays can introduce the burst of the decoherence errors that are hard to correct using the what a standard error correction technique. So this contributes towards our inability to represent the meaningful real life problem on a quantum computer. So furthermore, there is no uniformity in the underlying quantum computing hardware. Currently, various companies are pursuing different approaches towards building a quantum computer. For example, quantum annealer, like analog quantum computer, and a universal quantum computer, so on. So this is very similar to how we had multiple transistor designs in the initial days of computing. As a result, it's only possible for certain problem to be efficiently mapped into the specific types of underlying quantum computing hardware. So the research into solving the decoherent problem and designing general purpose quantum computers is somewhat is ongoing, and we are still about the 5 years away from solving meaningful problem on a quantum computer. In the meantime, we may anticipate the deployment of both the quantum and the classical computers in a hybrid manner to provide the computational efficiency. That's very important as the research is going on. So next, how the quantum computers are being deployed. So whenever we are talking about the deployment of quantum computers, in that case, the quantum computer, it requires the customized hardware. Today, only the big hyperscalers and a few hardware companies are providing quantum computer emulators, as well as these limited sized quantum computers as a cloud service. So that's why the quantum computers are presently being targeted for the problems that are compute intensive and not a latency sensitive. And also today's quantum computer architectures are not mature enough with that respect to the handling large data sets. That's why as a result, in many cases, the quantum computer is typically deployed along with a classical computer in a hybrid manner. Even though a quantum computer itself does not consume much power during the computation, it requires a specialized, we may say the cryogenic refrigerators to maintain low superconducting temperatures. That's why the current predictions show that there will be a fixed cooling cost with very little incremental power cost as a number of qubits increases up to the certain limit. So, however, one will need many of such cooling refrigerators to support the computers that provide the millions of qubits. So that's why the current we may say the cryogenic refrigerator consume around 24 kilowatts per unit for approximately 1000 qubits. So that's why this power budget does not include the power for the classical computer, storage and networking hardware surrounding the quantum computers. So that's another very important point. That's why based on that only the quantum computers are being deployed. And the next thing is what are the real world applications based on that quantum computing? So whenever we're talking about that real world application, here the exponential growth in computing the power that comes with that development of a viable quantum computer looks set to the revolution of the wide range of industries and applications. So that's why the many computing applications with the large data sets, that's why we come up with that big data and other things are poised to benefit from that advantage of the quantum computer and much what the world does, that is based on the principles of mathematics from the simulation to applications like that. So that's why the quantum computer with a huge computational power are ideally suited to the solving the problem, this kind of problem. So the first problem that create the world of opportunity across the almost every aspect of modern life. The first one is a healthcare. So under the healthcare, first point is a research. So actually, whenever we are talking about the real world application under the healthcare, the research and some kind of diagnostic, some kind of treatment. So all the way, this what the quantum computing applications is based on the healthcare in the research in the sense. First, actually the classical computers are very limited in terms of the size and complexity of any kind of molecules. They can simulate and compare, like even for the drug development and discovery of drugs and everything. But if we have an input size is n being the number of atoms in the particular researched molecule, the number of possible interactions between these articles is exponential. So that's why that is very useful. That's why the quantum computers will allow much larger molecule to be simulated. That's very important in terms of the healthcare application, mainly for the research oriented applications. That's the thing. That's why at the same time the researchers will be able to model and simulate the interaction between the drugs and all like 20,000 plus proteins that encoded in a human gene, that is leading to the greater advancement in pharmacology like that. The next second very important application based on the healthcare is the diagnostics. So here, with the help of the quantum technologies would be able to provide the faster and more accurate diagnostics with a variety of applications. That's why the boosting that AI capability, that artificial intelligence capabilities with improve that machine learning algorithm. That's something that is already being used to aid the pattern recognition and some kind of pattern matching and other thing. And another very important applications, very particularly for the diagnostics, is nothing but high resolution MRI machines will provide the greater levels of detail and also useful for the clinicians with the screening for the diseases like that. And third thing is the treatment, how we are providing the treatment, very particularly in the healthcare domain, based on the quantum computing in the sense in actually for the treatment purpose, we are actually we are targeted, we are come up with some kind of targeted treatment such as radiotherapy. That is, it depends on the ability to rapidly model and simulate the complex scenario to deliver the optimal treatment. That's why in that case, the quantum computer would enable the therapist to run more simulations in less time. That is helping to minimize the radiation damage to healthy tissues like that. So that's a very important. That's why that the quantum computing is very important in very particularly for the healthcare application in terms of the research, diagnostics, and even for the treatment. And second important application is the finance. So whenever that we are talking about the finance, the first application based on the finances in terms of the automated and high frequency trading. So that's why here the one potential application for these quantum technologies is algorithmic trading. So the algorithmic trading is nothing but the use of complex algorithm to automatically trigger the shared dealings that based on a wide variety of market variables and other things. That's why the advantages are especially for the high volume transactions are significant in that automated high frequency trading. And second application based on the finance is for fraud detections. So whenever the fraud detections, how that the quantum computing will be useful in the sense like the diagnostics of healthcare, the fraud detection is mainly depend on the pattern recognition. So in that cases, the quantum computers would deliver a significant improvement in machine learning capability. That's a somewhat it's reducing the time taken to train the neural network and improving the detection rate also. That's a very, very important. And third important application is a marketing based on the quantum computing. And whenever we are talking about the marketing with the quantum computing, the big data analytics is very, very important. So that's why the quantum computers will have the ability to aggregate and analyze huge volumes of consumer data from a wide variety of sources. So that's why the big data analytics will allow the commerce and government to precisely target the individual customers or any with the communications tailored to their preferences, helping to influence the consumer spending and outcome of that. What are the what outcome of that election? Outcome of that. How what they choosing, so the outcome of the result, so everything they make it in that marketing through that big data analytics with the help of the quantum computing. And fourth important thing is a meteorology. So in that meteorology, actually, we are more accurate for the weather forecast. So with so many variables to consider, that accurate weather forecast are difficult to that produce. So here the machine learning using quantum computing or quantum computers will result in improved pattern recognition, that making it easier to predict the extreme weather events and potentially saving the thousands of lives in a year. And even in the some kind of climatic changes, that also able to generate and analyze the more detailed climate models that providing the greater insight into the climate change and how we can mitigate its negative impact and everything. So that's another important application. And fifth important real world application for the quantum computing is the logistics. So whenever we are talking about the logistics, first most very important thing is the increase in supply chain efficiency. So increase the supply chain efficiency is nothing but here actually all the way we are improving the data analysis and modeling will enable a wide range of industries to optimize the workflow that are associated with even the transport, some kind of logistic and supply chain management and so on. So that's why the calculation and recalculation of this kind of optimal routes would impact on the applications as a diverse, as a traffic management, some kind of fleet operations, air traffic control, that freight and other kind of distributions and so on. So this is a very important application that's in terms of logistic based on that quantum computing. So these are the real world applications. These are the real world applications for quantum computing. So that's that's a very, very important in terms of healthcare, finance, marketing, meteorology, and logistics. So these are the these five applications based on the quantum computing. And next, how are they getting the quantum computing ready for prime time? So here, yeah. So here many large computer companies are investing the billions of dollars into building the quantum computers. Similarly, many academic institutions are also investing a lot of money to brain power into this area. But the current generation of quantum computers need to be managed by expert staff due to their specialized hardware and some kind of cooling requirements and everything. So as a result, in a near future, quantum computing functionality will be mostly offered as a cloud service. That's a very, very important thing. However, there will be a customers who will want to deploy their data and host the classical computing and storage portion of their overall architecture in their own private data centers, or that any kind of cages in a collocation facility for privacy and control reasons. And these customers would like to leverage the quantum computing functionality from a service provider. So that's why just see that this figure, actually this is actually this figure that highly interconnected the collocation data center platform, such as it's called as a Equinix data center. It allows the both enterprises as well as the quantum computing service provider to have the multiple hybrid development, hybrid deployment that options. So that's why here the quantum computing as a service based on the public cloud data center or public cloud data provider. So that's why here with the help of that quantum computing ready for the prime time. So that's this overview. So the final thought in conclusion, actually we are in the initial stages of the era of hybrid quantum computers, where the classical computers offload a certain types of processing of quantum computers with a limited number of qubits. We believe that this will be in the norm of that quantum computing for the next 5 years before non-hybrid native quantum computers containing thousands of qubits that start for solving any kind of real world problem like that. So with this short note, actually just I conclude my session. Thank you for your attention. Thank you so much.
Uh, Sir, okay. Thank you, Balakrishnan sir, for your valuable contribution to towards our knowledge. I'm sure each and every student who is over here, they have gained a very valuable insight from your keynote session. Thank you very much, sir.
Yeah, thank you. Thank you.
We can conclude the session now, sir, with your permission.
Yeah, yes.
Thank you, sir.
Any queries?
No, sir.
Yeah, thank you. Thank you.
Yeah. What the hell has started?